Okay, now we have to simply open the design modeler. Okay, and we discuss about the other things like a meshing and the quality of the mesh in the coming classes. Okay. Okay, so open the workbench. Okay, here we are going to be like there are various methods that you can use for the workbench. Okay, like you can take the fluid flow with a CFX, you can take the fluid flow with the Fluent also, and also you can take the separately every app like a geometry, and then you can drop the meshing on the geometry, and then you can drop the Fluent on the geometry, and it should be on the mesh, and then finally results. Okay, so both of them have the I have the different benefits. For example, I can have the different geometries. I can make the two geometries, and then I want to make them mesh in the one single window, or maybe the geometry is same. I want to make the different meshes, and I want to compare the different results. So there will be different meshing apps there, like a three meshes, three Fluent apps will be there, containers, and then I can compare all three results in the one single container for the CFD post. Okay, so it depends on the what is the requirement there. So let's go with the standard procedure of having the single container that contains everything there. Okay. Okay. Once you have like made the file, then the first thing that you have to be doing is that you have to save your project file. Okay. And where you should be saving the file, it should be in your working folder. Okay. Let's say this is my course folder, and mastering ANSYS CFD. Okay. And this is going to be the Laminar pi flow. Okay, so this is the one way, and if I go to the that folder there, you will see that this contains the one file that is the workbench project file wbpj here, and it contains the same name with the underscore files. This contains the files. So dp0 is the where folder where we have the files, and then in the triple F we have the design modeler first field is over here. Okay. Now, if you take a look here, you will see here, if I click here, you will see that the geometry component is a geometry 1 component ID, directory name is a triple F. So, every detail is given there. Okay. So, double click here and make the geometry file here. This geometry is going to be very simple. This is a very simple pipe. Okay. Okay, choose XY plane or any plane you want to choose, and go to sketching mode, and click on circle, click on the locate, and make sure that the P symbol is displayed there. If not, then you can go to the constraints, and auto constraints, turn on the global and cursor constraints there. So this cursor will take the snap to the nearest possible location. So point will be P, and any curve, even the axis they will be curved. So you will see the C symbol. Okay. So this should be there. Okay. So we have the one circle, and here. Okay. And before that, you should be choosing the your units. For example, meter is right now our unit. So maybe the units were millimeters or inches or the feet. Large model support is required when the model is extended over the some level. Okay, that I discuss in the some other courses when I go for details about the design modeler. Okay. Okay, so now put the dimensions here. Diameter is the dimension we are going to be putting here, and this is going to be the 1 meter. Okay, now you can see the dimension is like a very large, and geometry is very small. So you can move it like this. Okay, you can zoom and you can make it closer, wherever you want to make it, where it looks better. Okay. After that, I will go to the directly click on the extrude command. So we have the two options, sketching and modeling. Modeling means the 3D features and the sketching means the sketching, right? You are seeing here. So click on the extrude and this will take you to the modeling tab, and this will select this one sketch which is already there in the plane. So you can choose a sketch yourself also by clicking here and then click on apply. And two options are here, add material. This like right now for single body this will doesn't matter anything, but if there are two or more bodies, in that case if you choose add frozen, the two bodies will not be merged automatically when they are overlapping. Okay, they will not be merged automatically, and in the add material they will be merged automatically. Okay, so the pipe length is 40 meters, so put it over here, and now it should be showing you the preview. Okay, the third dimension of 40 meters should be now visible to you. Now in order to complete the operation you have to click on the generate. So in the 3D features, whenever you want to like complete any operation except the sketching, any operation in the modeling tab, you have to click on the generate. Okay, and then once again you can save the project file directly from the particular app as well. For example, from the geometry, meshing, Fluent, you can save the project file. Okay, and one more important thing, whenever you want to share your file to the somebody, okay, like with me, you have to click on the archive. This will write down the WBPZ. So the previously file was WB PJ, which is like in our working folder, which is here. Okay, so that file is a WBPJ. So it's a Workbench project file. Now this is going to be the Workbench project file, but in the zip format. Means this will zip the file and it will become a single file. Okay, so click on save, click on archive. So there are two ways that you can send the file to anybody. Number one is that click on the Workbench project file WBPJ and then also the folder here. Okay, right click here, then add to archive. This will write down the zip file that you know very well. Okay, so that file you should send, or you should send the this WBPZ file. Okay, now opening this file is also very important, that how you can open this file. So one way is that you have to double click here and then save with some new name. Okay, or second way is that you can open the Workbench. Okay, it should have opened the file. Okay, it is opening the file, and one is like a blank project. Okay, just let me know that there are two ways that you can open that file. Okay, so once you open that file, directly double clicking there, then you have to save this file. Okay, save as, let's say, the ABC. Okay, and second way is that okay, second way is that you have to go to file menu and then click on import. Okay, click on import, go to working folder, and from here click on the WBPZ file. Okay, click on open. Okay, before that you have to save the with some new name. Okay, let's say this is the BCD. Okay, it is going to be same folder, and then go to the file menu and import and take this file. Okay, and now once again you have to save the file with a new name. Okay, because before that there was no project, now we have these files imported. So there are two ways actually. Okay, so you can open in any way. Okay, so now you can close them and open the the Workbench project file directly from here. Okay, so either you should be sending this file, the zip file, or you should send the zip file directly in the Workbench extension format. Okay, this is done by the Workbench itself. This is done by the WinZip software. Okay, now we are going to the geometry. Okay, so we will go through the different things here, but first thing is that I will complete the geometry and we will go through some basic meshing and first simulation. Okay, and that we will do very quickly. Okay, so now here select the inlet face, right click here and click on name selection. And this is going to be the our inlet and click on generate. Okay, so every time you have to click on the generate option. Again, the second boundary name is the wall and click on generate, and the third boundary is the outlet. Okay, here you can actually make the body frozen, and this makes the this body as a transparent. So that is done from here. Okay, and simply click on generate. Okay, this is now a frozen body. You can see it from the inside. Okay. Okay, secondly, you can display the colors based on the name selections as well. So by name selection, and you can have the different colors here. Okay, you can also display as a wireframe, shaded exterior, or shaded exterior with the edges like this. And from the view menu, you can also turn off the transparency like this. Okay, and here you can turn on the like exterior, shaded exterior and the edges as well, and you can also display as a wireframe. Okay, and you have the many graphics options like edge coloring, the face coloring, the free one. So many things you can do here. Okay, so now the geometry is made, you can save the file and directly go to the meshing. Okay, so the first mesh, we will just click on the mesh and then click on the, it will actually take you to the mesh menu and then simply click on generate. That's all. Okay, this is your first mesh, and this is sort of the hexa meshing. It's not a regular hexa meshing. By regular hexa meshing, I mean that the hexa meshing should have the equal number of cells on the opposite side. Okay. Okay, so what I mean by the hexa meshing types, so there are two types of hexa meshing that we will be creating. Okay, one is the mapped hexa, and one is the pave hexa. In the map hexa, what will happen is that the number of cells from the one side and other side, they will be equal, but definitely with the circular geometry this will not be possible because we will have the low quality on these corners. Okay, so that's why here without dividing geometry in multiple parts, the pave hexa is the best strategy. So right now, for example, here this corner will have the two faces, third and the fourth face will have the very like a large angle. So this will make the problem for the meshing. So that we don't want. So in this case, the pave hexa, like they are not regular hexas, so they can go anywhere from here to there, but they will create the hexas, and maybe occasionally there will be one triangle in the between. So like for example, this is the triangle, and this will make the element type as a prism. Prism is a like element type that will have the top and bottom as the triangle, and the other ones will be the hexas. Okay, the rectangle. So here you can see that the okay, that thing we'll discuss after running the first case. Okay, running the first case, then we discuss these all things. Okay, quality and everything. Okay, so now the first mesh is created. You can check the quality from here. The most important one is the orthogonal quality, and that is minimum is a 0.67, and minimum allowed by the Fluent is 0.01, and anything like a 0.05 is a good. From 0.05 to 0.15 is very good. Means that practically speaking, definitely one will be best, but practically speaking, the anything above 1.15 is excellent quality. But right now it is like a very high quality right now with us, and definitely we don't have any mesh in the boundary layer, so that we will not be worrying about right now. And as far as number of cells are concerned, so we have the 20,992 cells, and number of elements nodes are 20,992, and elements are 18,360. Okay, last step in the meshing is that you have to click on the update. So this will actually export the mesh for Fluent. Okay, and you can save the project file as well. Okay, so name selections are same which we taken from the design modeler, like inlet, outlet, and the wall. Okay, inlet is on this side. Okay, one more thing is that is important to tell you about the geometry here. So in the graphics properties, actually you can make the transparency. Right now it's a 1, but you can like make it transparent as well. Okay, so now it is transparent. If I go to the point 1, it will be almost like a okay, make it 0.1. Okay, this is transparent. Okay, so whatever value you want, you can like use there. Okay, okay, so we saved the file, and now I'm going for the setup. So double click on the setup and open the setup from the Workbench. Okay, so don't change anything because it's a very simple mesh. So we can now click on start. Okay, so here is the Fluent interface, and so in the Fluent, what we are going to be prescribing, the one thing is that we will be prescribing our boundary conditions. Geometry already is here, so no need to be defining length or the diameter, and the fluid properties. Okay, and before that, we will go to the general settings, pressure base. Okay, steady state, it's a steady state case. I will go to models, and from the viscous, I'm going to select the laminar flow. Okay, and I will go to material properties and click on the create edit. So this is the name of the property. So name can be anything. The important thing is the values. Okay, values of the these properties, density and the viscosity. So in our calculation, the density is 1 and the viscosity is equal to 0.01. So you should be putting the correct values. Okay. Okay, density is a 1 and the viscosity is 0.01 kilogram per meter second or Pascal second. They are both are same units. So click on change create. And then go to boundary conditions, and you can arrange the boundary conditions based on the zone types. Okay, here you can click on the inlet and put the value of 1 meter per second. That will be normal to boundary, means will be directly going straight. Okay, and click on apply. And in the methods, I will keep the default settings of coupled solver. Coupled solver actually will be solving I will explain in the theory part. So this will solve the continuum and momentum equation in a single matrix. Okay, I will keep the default schemes for momentum and pressure. In the monitors, I will reduce the value of the convergence criteria, or I can directly go to show advanced controls. So either I put the very low values here, or I don't want to at all, I want to check the convergence. So you can click on the none. Okay, and click OK. So this means that now solution will only stop when the number of iterations are done, or when we stop ourselves by manually clicking on the stop button on the bottom. Okay, now run calculation, and I'm going to solve this for 200 iterations, they are enough for this simple problem. Okay, and click on calculate. Okay, before that, it will also initialize the solution, but we should initialize either from the standard method from the inlet, or you can use a hybrid initialization. So I would recommend that hybrid initialization should be used because this uses the simple differential equation to initialize the flow field. Okay, so click on the initialize, go to run calculation, and also I would recommend that you should monitor some values, like important values, for example the point values on the some location. So for example, if I display my mesh, okay, so let's create the one point on the towards outlet, and that will be around like a 35 meters. Okay, 35 meters in the z direction, and x and y both will be 0. So surface and the point, and point is at the x0, y0, and z is equal to 35. So you can say the point z 35 meters. Okay, click on create and close everything. Okay, now from report definitions, I will right click here and click on the new and surface report, and I'm going to be using the vertex average because this is the point, and for the point we should be making the vertex average. For the lines we are going to be making the line average. For faces or planes we are going to be making the face average or the macro average. So for the like a single point, it should be a vertex average, and where it is on the point z35, and what we want to monitor, the velocity. So you can write down the name as the velocity at z 35 meters. Okay, you can also print to console means on the screen, and it will make the one file that you can use in the Excel to open and plot that file, and one will be directly on the screen as a plot. Okay, now click on the OK and click on calculate. Here you can see the convergence, how it is going, and secondly you can see the convergence on a point. Okay, and this shows that the velocity is coming out to be the 1.6, around 1.6 or 1.55. Okay, here is our first simulation. It is done now. So it completed 200 iterations, and that's all. Okay. Now the first thing that I want to display is the pressure contours. Okay. So on the wall, and uncheck the global option. Total pressure drop is equal to the 134 Pascal. Okay, so 134 pressure is the total drop in the pressure. But if you remember, I told you that the pressure drop that we calculate for like a 40 meter per second, 40 meters length, this is 12.8. And why so? Because definitely the analytical part that is not covering the developing region, so that is not like correctly making those values there. So what is the idea? Idea is that we should make the delta P values for the when the flow is becomes fully developed. So how to access the flow is fully become developed? That is by plotting the velocity on the center line. Okay, that we are going to be doing here. So in this case, I would suggest one thing. Let's create the plane at the x is equal to 10 meters. Okay, and because we already calculated the analytical solution at the x like for 30 meters, so we can compare them very well. Okay, so that plane I will create through isosurface, and we have to create the constant surface of the mesh, and it will be on the constant z axis, z coordinate. So this will be the xy plane actually. Okay, and I'm going to create that plane at you can compute here, and it will give you the range of the z coordinate. So it's from 0 to 40 length of the cylinder. So let's make it 10 and click on create. Okay, And now go to surface integrals, and here, because the static pressure is area dependent, so I will use area weighted average at the outlet and z coordinate 4. You can name it like you can say it is the z plane at the z is equal to 10 meters. Okay. Okay, so you can see that the pressure drop, because outlet will be 0 and at the z coordinate 4, that is over here. Okay, I'm not displaying the inlet. So what we are doing is that, okay, let me change the color also. Okay, the new surface. Okay, that color we can change. What I want that, okay. So this is these are two surfaces, okay. And just for your knowledge, if I display the wall, I can actually make it like this is the over here, okay, at the 10 meters, okay. So I can make it transparent. So I can go to compose menu and display the mesh, I think from the display menu here, from the domain, okay. Okay, now the names will appear. So on the wall, click on display and turn off the edges, perimeter edges, lines and nodes, and make it transparent. Okay. And you can also display the inlet. And okay. So here we have this plane that is at the z is equal to 10 meters. So from 10 meters to the 40 meters is a distance of 30 meters. So here pressure drop is 9.57. And if you compare with the analytical solution for this much length, the analytical solution gives you, because this is a fully developed flow, so in this case analytical solution and CFD solution will match very well. So 9.6 and 9.57, 9.574. That's almost like a 9.58 and very close to 9.6 Pascal. Okay, so you get the idea that this equation was developed for the fully developed flow, and if you try to use it in the developing region, that definitely you will get the more errors. But even if you like compare data between inlet and outlet, this is a drop of 13.28, and if I assume whole pipe is the fully developed flow, so 12.8. So this much error is there. And why this is so? Because this is a region where the pressure is drop is non-linear. Okay, that's why we have the error. Okay, and that is not like we cannot calculate that in through the like delta p by delta x is equal to constant. That is not possible on this region. Okay. Now, if you compare the wall shear stress, so we can also find out the wall shear stress. So for that, we need to find it out on the some point maybe, okay, some point maybe, or the line. So that line we can create on the periphery of our circular cylinder. So I will go to the create and isosurface, and this time I will choose the wall, and I will choose again the mesh and same z coordinate. Okay, so let's make it at 35. So it's a z coordinate, and this is going to be the line at z is equal to 35 meters. Okay, go to the surface integrals and from the results, and here I will be making the vertex average because it's a line, it's a combination of the points. So vertex average and on this line, okay, click on compute. So the value is the 1.59. It's not definitely correct, okay. So let's make it like a line on the along the length of the pipe, okay. That will give you the better results, okay. So create and iso surface mesh, and this time choose a constant x, okay. Choose a wall, click on compute and click on create, okay. So this line okay, there are two lines here, you can see top and bottom, but I just need the one line. So I will go to the create and this time I will use the iso clip, okay. So iso clip and I will choose the again the mesh, and this time I will use x coordinate 6, but this time I will clip them in the y direction because one is at the y is equal to plus 0.5, one is at the y is equal to minus 0.5. So if I just change the values little bit, very smaller values on the negative side, it means the range will be offset and the line will not be selected now. This only line that is remaining now in the iso clip will be top line. So simply click here and now display. Okay, this line is over here. This line, okay. And okay, one more thing is that this was a static pressure, okay, sorry. So let's go back and make the correct values, okay, here. So wall fluxes, wall shear stress, and here click on the compute. So it's a 0.078. Okay, so now this makes a sense, okay. So value from the analytical solution is the 0.08 and value here is a 0.0787. That's a 0.079 almost. So let's check the error. How much error do we have here? 0.078 minus 0.08 divided by 0.08 into 100. It's only 1.6% error. Okay, if you display the xy plot on the y clip coordinate and along the z axis, so make it z is equal to 1 and x and y both 0, and go to wall fluxes, wall shear stress, click on save plot. So initially when the flow was developing, definitely we have the like a nonlinear region. Then the flow, once flow is developed, then I told you before in the theory part that the wall shear stress will be constant because the gradient will be constant because velocity not changing. That's the definition of the when the flow is fully developed there. So if I take a look here, the value is 0.79, the same value, okay. Okay, now I'm going to create a line and that line will be on the center. Okay, so it will be 0, 0 in the x and y and 0 z and 0 second point on the z will be 40. So line, this is the axis line, okay. Okay, now click on the xy plot and put the name as the pressure along the center line, okay. This will be along the z axis, so put the z axis here and click on the we have the line axis, okay, and click on the save plot. So again you can see the same pressure drop like you expect here, and the same was displayed in the line plot here as well, this one, okay, same thing here. And next graph that I'm going to make is of the velocity. So it's a center line velocity and 0 and 1, and that is along the line axis, okay. And we know that the velocity at the center is maximum, okay, from the analytical solution. here. So when the flow becomes fully developed, then the velocity is developed there, then the velocity should not change. Velocity should not change any location. Here it's the 1x, second x, and it is true for the any radial location. Definitely on the radial location they will be changing, but along the axial direction at the same radius they should not change. Okay, this is the definition of the when the flow is fully developed. So once the flow is fully developed, then we should be getting the maximum velocity at the center. And because we know the formula that the U maximum is twice the U average or the U mean or the velocity we provided on the inlet. So it means that if I display the velocity on the center, it should be equal to 2 into U average, which is 1. So it should be 2 meter per second. But here we are getting the values which are actually low. It is around 1.9, and this is because of the mesh density there. Okay, this is very coarse mesh, that's why we are getting this thing here. Okay, but still it's a better than the tetra meshing. Let me tell you, any hexa meshing for the internal flow will always give you better results than the tetra meshing because of the low number of cells in the core region. Okay, so we have plotted the velocity, we have plotted the these parameters. Now we are going to compare the value of CF. Okay, so what we determined is that the CF is equal to 0.16 and F was equal to because the formula is this one, and the F was equal to 0.64. Okay, so here we cannot directly find out the value of the F, so we can find out the value of CF, and from CF we can actually find out the value of the F. Okay, and that's a Darcy fraction factor that you can actually you can find it out from this graph. Okay, so if I go to the results here, that the CF is equal to the 0.16. Okay, so same way surface integrals, and this time, but before that we have to provide the reference value. So what reference values we need? We need the for CF formula is wall shear stress divided by that's a calculated from the Fluent, and the 1/2 is the constant value density and velocity square. So I will take them from the inlet. Okay, and that values are the 1 and 1. So you can see the velocity is 1 and the density is a 1, and that's what we needed. Okay, so be careful. The dimensional quantities, they are calculated by the Fluent, but non-dimensional quantities are again calculated by the Fluent, but not from CFD. It is like dividing the main variable by the some quantity that will make it non-dimensional. So that requires a reference values, and you should put the correct reference values in the panel here. Okay, so skin fraction coefficient, and click on compute. Its value is a 0.157, and the value we are getting from the theory is the 0.16. So almost like a negligible error. And that I can also plot on the XY plot. This is a CF plot. Okay, so same line, that is a clip Y coordinate, and here I will choose the wall fluxes and skin fraction coefficient, and that is along the Z axis. So put the Z1 and X and Y 0, and click on the plot. So you can see the value is like a 0.157. Okay, so 0.157 minus 0.16 divided by 0.16 into 100. So error is like a 0.048%. Okay, so and now let's make a new plane on the center location. Okay, this is the center plane, and it is a constant mesh and constant you can make it like a constant X or Y. It will work very well because this is along the circumference, and circumferentially flow is same. Okay, no change there. Okay, so it is on the middle location 0. So create. Okay, so if you display the mesh, this plane I was talking about. Okay, so here I'm going to be displaying the what I'm going to display the pressure contours. Okay, So the contours and display only the like let's display the wall as well. Okay, so wall, inlet and outlet. So this is a transparent, so we can see it directly from the inside. Okay, and it is not the global range, so uncheck the global range and click on save display. Okay, you can also make it bended, and from color map you can change the number of colors map size like a right now we have the 100 levels of the contours, and now you can display like only 20 levels. You can also display them in the old style, that is a BGR, blue, green and red, and that makes more sense actually. Okay, we have the like we can clearly see the bands. One more like that is my favorite is the arrow is also a very good color map like here. Okay. Okay, second thing is that you can change the legend as well. For example, here I can only display the variable name, and I can display the floating, and you can change the size of the color map as well. So make it point. I usually speak. I take the 0.8 and the 4 here. Okay. So you can skip the levels like this. Okay. Default is 9, and you can also change the precision as well. Okay. So now you know that the how to post-process results, how to run the case, how to make the mesh, how to make the geometry. There are few things that I want to discuss, and then we will go further different meshing algorithms, okay, and discuss about the meshing quality, meshing methods, everything will be discussed in detail. Okay. Okay, here I'm going to display the vector plots, and you can see that the velocity is following the parabolic velocity profile in the center plane. Okay, and maximum velocity is 1.92, and if I change the scale to the 0.2, okay, let's make it and uncheck the global range 0.5. Okay, because we have a very less number of cells, that's why you might not be able to see them very clearly. Okay, so but they are there actually. Okay. Okay, now I'm going to make the one line. That line will be the line on the location where I can plot the radial profile. Okay, that is the profile we have. We have here this profile. Okay, so for that I will make a new line. Okay, and that line will be at the z is equal to 35 meters from the inlet, and r will be minus 0.5 to the plus 0.5. Okay, this is the radial line at z is equal to 35 meters. Okay, I will now again plot another xy plot. This is the radial velocity profile. This time this will be along the y-axis, so I will put the y and the velocity, and click on the line here. Okay, click on save plot. Okay, you can shift them on the y-axis. Okay, like this. Like this. Okay, so this is same profile as we have here. Okay, now I will export this profile into Excel, and we will compare them side by side. Okay. Okay, so we have to write it to the file, and click on write. Velocity profile, and on the like a very rough mesh. Okay. Okay, now open the Excel. Go to data and import from text file. make it all files, and here this is the velocity profile rough mesh. Okay, space is there, sometimes comma work, so you have to see which delimiter is going to work for your case. Okay, now copy the equation. Okay, so start from the point 5 and equal to the 0.5 minus 0.05. This is equal to the 2 into velocity average, that is equal to the 1 meter per second. And if you make a one extra cell and where you write down the velocity there, so whenever you change the velocity, that will be updated automatically. That's a suggestion here. And into 1 minus r square. So 1 minus, give the one extra bracket here. So this is the, okay, let's put the values like here. Okay, so let's put the u average. It's a 1 meter per second. And capital R is equal to 0.5 meters. Okay, so now the formula will be very much simpler. Okay, so it is equal to the 2 into u average multiply 1 minus bracket, so it is the r square. So r square, and this is the actually number 9. Okay, divided by this capital R square. Okay, I will put the two extra brackets to be on the safe side. R square inside the bracket and capital R square also inside the bracket. Okay, now you have to put the dollar symbol so that this cell will remain the fixed one. And similarly, for the velocity, dollar sign should be there. Okay, let's check the formula, and the formula is that's twice the T2 is over here. Okay, and then it's a 1 minus r square, that is the cell number n9. Okay, and divided by st3 square. Okay, so now you can drag it, and the value of velocity u average and r will be fixed here. Okay, inside there. So now you can plot the velocity profile. This is an analytical solution. So insert, and second one is going to be the second value, that is from CFD. So first is the analytical solution, and second one is the CFD. Okay, So here we can like change the layout of the graph. This is the radial position. And this is the velocity. Okay, this is the radial velocity profile. And one more thing that I want to show you is that, for example, we have displayed the contour plots. Okay, you have to uncheck global range because this global range will be range for the complete geometry. And okay, I think that my surfaces are now missing. Okay, so I told you that you can go to view menu and from here click on the wall, click on display, and turn on these options, turn off these options there, make it transparent. And you can also change the colors, for example, like this. Okay. Okay. And if you turn off the like option for the outer faces, then the face that is like is facing you will be turned off. Okay. And if you click on the overlays, then everything that you are going to display afterwards, they will be recorded here. Means that everything will be there. For example, you want to display multiple contour plots, they will be saved here. Okay. Okay. Now go to graphics and contour number 3. Okay, this time don't turn on the draw mesh because already mesh is there. If I do it, then they will be duplicate copies over there. Okay, so but that's good thing is that we can delete them actually. Okay, so once you do the overlays, then don't try to display that thing once again. Okay. Okay, so here I will change to the variable only and the floating 0.8 and 4. Okay, so now the most important thing is that definitely you need to have these pictures in a good quality. So first set its view that you think is you want to display in that way. Okay, so go to the file menu. From here, click on save picture. So here you can you can export the picture in the various types. And here you can have the landscape orientation and the white background. So you can click on the preview. This is how the mesh, the picture will look like. Okay. So from here you can get the idea. Like if I make it over here. So this is some part is actually is like going on the bottom side. So now it's all right. And if you want to turn off the white color, then it will have the gray color on the background. And in a similar way, you can also have the picture type as the other way around. Okay. So I think landscape is better. Okay. So finally, you can save the file, save this picture file. Let's say over here. So this is the pressure contours center plane. Okay. And then if you want, you can like insert them to the your presentation. This is the one important thing that I want to discuss here. Okay. Like this.